In chapter 9, we are going to examine reactions of alkenes. There is a large number of very diverse reactions of alkenes, and you are supposed to be familiar with all of them. In general, what will happen is on an exam, you will encounter a reaction you haven't seen before, in a sense that that particular set, that particular combination of substrate and reagent would be something you haven't seen before. But based on your knowledge, you should be able to figure out the outcome. Typical questions could be about, of course, what is the reaction product, but also you could be given starting material, substrate, alkene, and product, and asked what was the reagent. Or you could be given reagent and the product and asked what was the starting material. So those are three typical types of questions. You should be able to classify reactions of alkenes. So functional group is double bond, carbon-carbon double bond, and that's where the reaction occurs, on carbon-carbon double bond. So when you classify them, those are reactions that proceed through carbocations as intermediates. Those proceed through free radicals. So this would be shown here on the right. Where reaction with electrophile gives carbocation is reaction intermediate. Those that proceed through free radical as reaction intermediate, so reaction to free radical is radical intermediate, and those that proceed through cyclic intermediates on transition states. And then there are other types of reactions that we cannot classify here, that are reactions such as catalytic hydrogenation, which means addition of oxygen in the presence of a catalyst, addition of hydrogen in the presence of a catalyst, and oxidation reactions. So I went a little bit ahead. Oxidation reactions, that would be addition of oxygen to double bonds. So in case of carbocation as reaction intermediate, some electrophile, and the most common electrophile in organic chemistry is proton. Electrophile adds across a double bond to generate carbocation. And now that carbocation is a new electrophile, which reacts with a nucleophile to give a product. First addition of electrophile across a double bond is slow step. Second step is product determining step. So slow step is rate determining step. Second is product determining step. At this time, this may not mean much to you, but later you may see the reason why this product determining step. When more than one product can be formed, that's determined in this product determining step. So this is typical reaction, addition of hydrogen bromide across double bond, and this is in general terms. Hydrogen halides are typical class of compounds that add across a double bond in this manner through carbocation as reaction intermediate. So hydrogen proton adds first to give carbocation, and then halide anion combines with carbocation, halide nucleophile to give the final product. So when you see a reaction of an alkene with hydrogen halide, you should be able to figure out what is the product. There is limitation to this reaction, and limitation is that hydrogen fluoride does not add across double bond cleanly, so we obtain complex mixture products. That's not preparatively used for reaction. So only hydrogen chloride, hydrogen bromide, and hydrogen iodide add across double bond to give corresponding alkyl halides cleanly. And then you see the mechanism. You should cover it on your own. Typically, we study mechanism in gas phase, even though we don't carry out reactions in gas phase, because it's easier to study in gas phase. We don't have to worry about role of solvent. But reactions are usually carried out in solution, which makes it more complex because then solvent also interferes. And this is very important, relative stability of carbocations. We classify carbocations according to degree of substitution of carbocationic or electron deficient carbon. So we classify carbocations as methyl cation, primary, where carbon has only one substituent, secondary, carbon with two substituents, and tertiary, carbon with three substituents. The order of stability is such that tertiary carbocation is by far the most stable, then secondary, and then primary has low stability. It has such low stability that often it doesn't even form, and the reaction may sometimes proceed through a different mechanism, and rather than carbocation, but it could form. And then methyl, by far the lowest stability. So that's the order of stabilities. Methyl the lowest, then primary, then secondary, tertiary, the highest. We explain stability of carbocations through a phenomenon known as hyperconjugation. That's form of electron delocalization. Carbocation has carbon that is sp2 hybridized and electron deficient. It has empty p orbital. So when neighboring carbon has a substituent, then that substituent must be, substituent is anything other than hydrogen. So that substituent must have another bond, carbon-hydrogen or carbon-carbon. That bond aligns with empty orbital. And electron pair from that bond, bonding electron pair, delocalizes or spills over into empty orbit. Such delocalization and delocalization of electrons in general stabilizes the system. System could be molecule, ion, or radical. So it stabilizes the system because delocalization reduces repulsion between electrons. Two electrons that make up electron pair are negatively charged and they repel each other. So if they can spill over, delocalize into another orbital, they are spread over a larger region of space, and so their electrostatic repulsion is minimized. And the whole system becomes more stable. And in addition, this carbon that used to be electron deficient now is less electron deficient because part of its electron deficiency is satisfied or compensated for by this electron pair being spilling over into this empty orbit. So in case of primary carbocation, only one such bond from the substituent can align properly with empty orbital to result in hyperconjugation. In case of secondary, we have two such interactions, one from each substituent. So that's why secondary is much more stable than primary carbocation. And tertiary, that's maximum degree of stabilization because all three substituents have bonds that are delocalized, where we have stabilization through hyperconjugation from three bonds. That's why tertiary is by far the most stable. In methyl, there is no possibility for stabilization to hyperconjugation, so that one is extremely unstable carbocation. So you need to know what is the phenomenon of hyperconjugation and how it operates, how it is responsible for the observed stability of carbocations. We have just examined regioselectivity in chapter 7. So regioselectivity of substitution of alkanes with halogens. In case of addition reaction across a double bond, there is also regioselectivity. In this case, regioselectivity has to do with addition of hydrogen halide, HCl, HBr, HI across a double bond. Now, the expected ratio is 50-50 because now we have addition across double bond. And so addition means that hydrogen adds to one carbon of the double bond and halogen, chlorine, bromine, or iodine to the other. Statistically at random, because hydrogen adds first, hydrogen could add to carbon 1 or carbon 2 with equal probability at random. So 50% odds that hydrogen will end up on carbon 1 or carbon 2. If hydrogen ends up on carbon 1, chlorine must add to carbon 2. If hydrogen adds to carbon 2, chlorine must add to carbon 1. So it's the first step that determines what the product is going to be. And so it's 50-50. If you get anything other than 50-50, reaction is regioselective. And indeed, it is regioselective because we end up with more substituted hydrogen halide. And that's been observed a long time ago in 19th century by Russian chemist Markovnikov, who formulated Markovnikov rule. This was an empirical rule. He had no idea about reaction mechanism or anything like that. Simply, he did a lot of reactions, and based on the outcome, he formulated his rule. So his rule states that in an addition of a hydrogen halide or water to an unsymmetrical alkene, Unsymmetrical means two carbons are different, so two different products are obtained. To an unsymmetrical alkene, the hydrogen or electrophile in general adds to the carbon atom of the double bond that is bonded to more hydrogens. And so when you look at this carbon is CH2. It's bonded to two hydrogens. This one is just carbon. There are no hydrogens. So this carbon has more hydrogens. Hydrogen of HCl will bond to carbon that has more hydrogens. And that's the major product. It becomes CH3. And of course, by default, chloride or chlorine ends up on carbon 2. Now we look at reaction mechanism and we explain that through stability of carbocations. So as hydrogen adds to carbon that contains more hydrogens, that's actually less substitute carbon. So hydrogen adds to carbon that contains more hydrogens. That gives more stable carbocation, more substitute carbocation, secondary. If hydrogen were to add to carbon that contains fewer hydrogens, that gives less stable carbocation, primary. So that's why we observe this regioselectivity. Hydrogen adds to less substitute carbon because that gives more substituted, more stable carbocation. And then combination of nucleophile with, or reaction of nucleophile with that carbocation, more stable carbocation, gives the major product. Regioselectivity is not very high. We get mixture of the two, but regioselectivity is noticeable. Frequently, ratio of the two is something like 70-30, 70% 2-chloropropane versus 30% 1-chloropropane, or maybe 80-20 or something like that, depending on the conditions. On the test, you will usually be asked which one is the major product. And so if you have to write down the name, for a reaction like this, you would say product is 2-chloropropane, because you'll be asked what is the major product. So which one forms in larger amount. If you are given both, then you have to be able to figure out which one is the major, which one is the minor. One that forms in larger amount is major, one smaller amount minor. And so you can, again, either apply a Markovnikov rule or, even better, consider reaction mechanism. So let's say addition of hydrogen iodide to this compound, 2-methyl 2-butene. So this carbon has only one hydrogen, but this one has none. So hydrogen will add to carbon with fewer hydrogens. That means iodine to the other carbon. Or hydrogen adds to less substitute carbon so that tertiary carbocation can form. If hydrogen were to add to carbon 2, secondary carbocation would form. So tertiary is more stable. That one will form, and iodine will bond to tertiary carbon. Major. The other one is minor. Don't be confused by rings. Same reasoning applies. So more stable carbocation forms. So hydrogen adds to less substitute carbon to give more stable tertiary carbocation, and that's major product. Minor product results of addition of hydrogen to more substitute carbon to give secondary carbocation, less stable. That's why it's minor. So rings, exactly the same reasoning applies. So don't be confused by rings. There are exceptions to Markovnikov rule, but you don't need to know them now. You study them in the second semester. So that's something that is a job for my colleague Elijah. And if and when he covers that, that's up to him how he's going to do it. Exceptions are listed here so that when you study that, you can come back to this chapter and review that and understand better when those exceptions occur. They will not be under this test, and you don't need to know them now. So this part is something you can skip. So second part of page 193, exceptions to Markovnikov rule. You can skip that now. That's not on the test now. When I cover that in the course, I go back and cover this at that time. But again, that won't be my course or my job. Addition of water and alcohols also proceeds through carbocation as reaction intermediate. And we need an acid catalyst, just a drop of an acid, like drop of sulfuric, phosphoric acid, maybe perchloric acid. And so just drop of an acid catalyst, and that results in very fast reaction. Again, hydrogen adds to less substitute carbon, and hydroxyl group adds to more substitute carbon. So in case of addition of water, it's elements of water, H and OH, that add across a double bond. H, hydrogen adds to one carbon, OH to the other carbon. OH ends up on more substitute carbon. Here is the reaction mechanism. First step, protonation is slow step, that's acid. That proton is a double bond. Major intermediate is more substitute carbocation. Reaction with nucleophile, water, results in formation of oxonium ion, and deprotonation of oxonium ion results in formation of alcohol, reaction product, and that regenerates the acid. See, deprotonation with water generates H3O plus hydronium ion, which then as a catalyst goes into first step. So now you can see what is a catalyst in organic reaction. Reagent in the first step and regenerated later, possibly in the last step of reaction. That's why you need very small amount of catalyst. It's not used up in the course of reaction. And of course, result of addition of water is corresponding alcohol. Alcohols add exactly the same way as water. And the only difference is now products are ethers. And again, just like water, on their own, alcohols don't react with an alkene. We need a drop of an acid catalyst. And with an acid catalyst, the reaction is very fast. It's done within minutes. And products are corresponding ethers. So exactly the same as addition of water. Basically, this substituent, methyl group, ethyl group, cyclopentyl, cyclohexyl, that does not participate in reaction. It's oxygen that adds to the double bond. So it's the same mechanism as addition of water. You just replace one hydrogen with this group of alcohol. And here is the mechanism. We have an example, one example. Let me quickly check if there are any questions, and then I'll go to reactions. I don't see any questions, so let's go back. So very important, yes, you should know the mechanisms. There could be questions about the mechanisms, like what is the intermediate, what is the electron flow, and so on. And also, it's a good idea to know the mechanisms because that's how you can predict reaction outcome and how you can predict if, let's say, rearrangements occur. So rearrangements here are basically changes in skeleton of the molecule in the course of reaction. And there are two types of rearrangements that are related to reactions of carbocations. One is hydride shift. So a carbocation, when it forms, may undergo hydride shift. So neighboring hydrogen takes electron pair. That's why it's called hydride. H minus, H with electron pair minus is hydride. Takes its electron pair, in the transition state forms a bond to both carbons, and then moves to the carbon that was originally carbocation. Now, carbon that hydrogen has left is new carbocation. So that's 1,2 hydride shift. And carbon does the same thing, can do the same thing. Typically, it's methyl group that shifts. In general, as a general rule, it's the smallest group that shifts. So when you have possibilities for different rearrangements, it's the smallest group that shifts. Hydrogen preferentially to methyl, methyl preferentially to ethyl, ethyl preferentially to propyl, and so on. So here is how it works. In case of compound like this, 3,3-dimethyl-1-butene, upon protonation, secondary carbocation forms. Now that secondary carbocation, if reaction is, let's say, with hydrogen chloride, you may expect, based on what you learned so far, that secondary carbocation would combine with nucleophile, chloride and ion, to give 2,2-dimethyl, 3-chloro-2,2-dimethyl-butane. But that's actually only minor product, only about like 3% of the product. Major product is result of methyl shift. So one of these three methyl groups, any of them, will shift, because 1,2-alkyl shift, to give tertiary carbocation. And that's why rearrangement occurs, see. We go from secondary to tertiary carbocation. So rearrangement occurs in the course of reaction of carbocations so that more stable carbocation can form. So typically secondary carbocation rearranges into tertiary. So whenever you see a secondary carbocation, whenever you are doing a reaction and as a result of going through the mechanism, you see that secondary carbocation has been generated, always check, is there a possibility it could rearrange to tertiary? Because if there is, it will rearrange to tertiary. And so as a result of rearrangement, you see now carbon skeleton is different. And now fluoride anion combines with tertiary carbocation, and you see the product is product with that has rearranged skeleton. So you started with 3,3-dimethyl-1-butene, but product is 2-chloro-2,3-dimethylbutene. So you start with 3,3-dimethyl and you end up with 2,3-dimethyl. You have to be able to name it and also recognize it when you see it. Keep in mind that rearrangement will occur only if more stable carbocation can be formed. So if that's not the case, then there is no rearrangement. So primary carbocation will not rearrange into another primary. And secondary, as in this case, will not rearrange into another secondary carbocation. Then you have only straightforward addition across double bond. So be careful about that. Sometimes when students learn about rearrangements, they see rearrangements everywhere and keep on coming up with rearrangements. In this case, of course, there are a lot of different rearrangements, but at this time, as you're only beginning to learn about this concept, the only rearrangements that you will encounter are rearrangements of secondary carbocation into tertiary, because that's the most common type. And so that's the only one that you should be on lookout for. Typically, as I said, secondary carbocation rearranges to the tertiary, but there is another important rearrangement that you need to know. And that's the rearrangement of small rings. Small rings are 3- and 4-membered rings. They have great degree of strain, as you may recall from chapter 4, first exam. And so for that reason, they always, as a result of rearrangement, undergo ring enlargement. So 3-membered ring, as a result of rearrangement, rearranges into 4-membered ring, and as shown here, 4-membered ring rearranges into 5-membered ring. That relieves angle strain. So remember that as exceptions. When you go to larger rings, 5 and 6, then rearrangements are more conventional, secondary into tertiary carbocation. If there is something different, then I will state that on the test. So then I may tell you this compound rearranges to this one and give you all the formulas if it's something you couldn't figure out. Now, this is also organic 2, and again, something I tell later students, go back to organic 1 and review it, and I would cover it. At that time, again, I don't know what is Elijah going to do, but this part will not be on the test. So again, if you're making notes, second part of page 196, second half, anything after rearrangement of 4-membered ring. Rearrangements of 3- and 4-membered rings could be on the test. That's a reasonable question. But what I just highlighted here, so this will not be. Again, these are coming attractions. This is something we cover in Organic 2 when we cover electron delocalization, chapter 17. And at that time I covered this and also tell students to go back and review this material. So one important aspect of my lectures or our meetings is also to tell you what to focus on, what you don't need to study now. So those would be carbocations. Another large class of reactions are reactions that proceed through free radical intermediates. And such reactions are addition of hydrogen bromide, actually, in general. History of this reaction is very interesting, but obviously I won't be going through it. We don't have much time. The only thing is that it was noticed that when addition of hydrogen bromide is carried out in typical solvents like dichloromethane, we get expected Markovnikov addition. Carbocation is reaction intermediate, and bromine ends up on more substitute carbon. But when reaction was carried out in diethyl ether, we get unexpected reaction, where bromine is on less substitute carbon. And that has been attributed to presence of free radicals in diethyl ether because they are common impurity in diethyl ether. And so this reaction now can be carried out. We do it, but we carry it out under free radical conditions, which means we add free radicals. Typical free radicals are peroxides. So this would be hydrogen peroxide, or dialkyl peroxides. Peroxides, under influence of light or ordinary ambient light, decompose on their own because oxygen-oxygen bond is weak to give oxygen radicals. And now these radicals catalyze the reaction. So the radicals, oxygen radicals, react with hydrogen bromide to generate bromine radical, and then bromine radical in propagation step adds across double bond to give carbon radical, which then reacts with another hydrogen bromide molecule to give the final product. And what you can see here is that more substitute free radical forms. Stability of free radicals is very similar to that of stability of carbocations. It's for different reasons. In case of carbocations, the reason behind observed stability is electron localization. In case of free radicals, it's more steric, groups that bump into each other. But nonetheless, the more substitute free radical, the more stable it is. So tertiary is the most stable, then secondary, then primary, and methyl the least stable. So same order of stabilities. So now, since bromine is the reagent, the species that adds first, not hydrogen, it will add across double bond to give more substitute free radical, more stable, secondary in this case. So it adds to less substitute carbon, and then free radical from more substitute carbon reacts with HBr to form a bond with hydrogen, and we end up with opposite selectivity. So under free radical conditions, hydrogen bromide adds with opposite regional selectivity. And we know that this is free radical reaction because we can observe formation of dimers. You may recall that from chapter 7. That formation of dimers indicates dimers, those are compounds with twice as many carbons as the starting material. That's indication that reaction is free radical. And this effect is called peroxide effect. And actually it works only in case of hydrogen bromide. Only hydrogen bromide in general can add under free radical conditions. That's because both propagation steps, first and second, must be exothermic for free radical reaction to propagate. If only one of them is not exothermic, if one of them is endothermic, it's unfavorable. And reaction then proceeds through alternate mechanism that is more favorable, and that's carbocationic mechanism. And so addition of HCl or HI proceeds only through carbocationic mechanism, even if we try to carry out reaction under free radical conditions. So this applies only to HBr. Now, there are some exceptions where we have been able to carry out reaction with HCl, but so I'm mentioning that in case you use some other textbook, you will not encounter it in this course, because I want to keep things simple. So only HBr, you should, even though it's not quite correct, but you should rely on that simplification, that only HBr adds under free radical conditions. And stability of free radicals, as I mentioned, is the same as that of carbocations. Tertiary the most stable, then secondary, then primary, and finally methyl. But the reason for that is steric. You see, in case of tertiary free radical, three substituents bump into each other, or tertiary compound. So when tertiary radical is formed, substituents get a little bit out of the way, and there is release of steric hindrance. There is less hindrance in the secondary and almost none in primary, and so there is less incentive basically for a molecule to form secondary or primary radicals. Okay. Let me see again if there are any questions. How about chapter 9? We are going to cover next section, which means cyclic intermediates. Oxidation and reductions are something we'll cover next day, and then all the exercises next day. So reactions that proceed through cyclic intermediate or transition state are third large class of reactions of alkenes. And by far the most important are additions of halogens, and in general those are additions of chlorine and bromine. Fluorine is too reactive, and typically sometimes reaction is explosive, while iodine is unreactive. So addition of bromine is often diagnostic reaction for presence of a double bond. So bromine adds across a double bond in such a way that each of the bromine atoms of the molecule adds to one carbon of the double bond. And that's a diagnostic reaction for presence of double bond. Because bromine is dark red-brown compound, and product is colorless. So we can actually do a titration and add slowly bromine to solution of alkene and see how much bromine has been consumed. And then calculate from how many moles of bromine have been consumed. We can figure out how many double bonds are in the molecule. And that can tell us something about degrees of unsaturation. For example, I can give you a formula of this compound. That would be C6H10. And then tell you it reacts. I won't tell you what it is. Just give you compound C6H10 reacts with one equivalent of bromine. That's 1, see 1 to 1. How many rings does it have? Now from this you know that it has 1, but you wouldn't know that on a test. How would you figure that out? Well, C6H10, you calculate number of degrees of unsaturation using formula I gave you earlier. There are 2 degrees of unsaturation. It reacts with 1 equivalent of bromine. Bromine adds across a pi bond, which means if it reacts with 1 equivalent of bromine, there is 1 pi bond. 2 degrees of unsaturation, that's total of sum of pi bonds and rings. If there is 1 pi bond and 2 degrees of unsaturation, that means there is 1 ring. And that's the ring. That's a relatively simple question. And here is the reaction mechanism. It's very important because carbocation is transition state, not an intermediate. Intermediate is bromonium ion. See this cyclic 3-membered ring with bromine. That's bromonium ion. And why it's important is that second bromine atom, this bromide nucleophile, attacks from the back, from the opposite side. And the result is that 2 bromines add to the opposite sides of double bond. Addition from the opposite sides of the double bond is called anti-addition. So 2 bromines add anti to each other, opposite sides of double bond. So it's anti-addition. It's not trans. Students often call that trans. No, product is trans. If you look at the product, 2 bromines are on the opposite sides of the ring, that's trans product. So product is trans, but addition is anti. So trans product, in case of cyclic compounds, cyclic alkenes, trans product is consequence of anti-addition. So make sure you know what anti means and what trans means. Don't mix up the two. 2 bromines, of course, end up next to each other on neighboring carbons, and that's called vicinal. When 2 groups are on the neighboring carbons, that's vicinal compound. In this case, vicinal dibromide. They are in vicinity of each other. When 2 groups are on the same carbon, that's geminal. And here are some additional examples. So bromination can be carried out in presence of benzene ring. It's not affected. If carboxyl group is far away from double bond, it can be carried out. If it's too close, then it interferes. Now, you will not be tested on these 2 examples. You'll be only tested on first 2, not on the last 2. I'm only showing you with the next 2 how complex organic chemistry could be and how functional groups could interfere with the expected reaction. But don't worry, you would never get something this complex on the exam. You're now only tested on straightforward reactions, addition of bromine across double bonds. And that this also shows you how do you figure out reaction outcome on a test. When you see something, some molecule that you have never seen before and it reacts with bromine, for example, you redraw the entire molecule and you simply add bromine across double bond. So what was double bond becomes single, and those carbons end up with bonds to bromine. That's all. Again, something like this, you would never have that on the test. It just illustrates complexity of organic compounds and organic reactions. Further example of why backside attack, why bromine has to attack from the back, why it's anti-addition, and why we end up with trans product. That has to do with orbitals, molecular orbitals that are available for reaction. Because any electron pair, free electron pair, has to add to a molecular orbital, to empty orbit. Addition of chlorine is exactly the same as addition of bromine. Exactly the same. The only thing is you replace Br with Cl. Same mechanism, everything is the same. And as I mentioned before, fluorine and iodine, those reactions are not preparatively useful. If we use water as a solvent, then things could become a little bit problematic because water is nucleophile and water would end and we end up with mixed addition. So hydroxyl group adds to one carbon and halogen to the other. Now we can actually add two different halogens, bromine and chlorine. So we can mix them. So there is actually exercise, I believe, either on the practice test or what I will do next day about this. So if we use halogen and then large excess of halide salt like sodium chloride or Cl2 and sodium bromide, then we end up with mixed addition. And of course we form, in this case, bromonium ion, and then the anion, fluoride anion, adds to more substitute carbon. That's because in case of, you see this bromonium cation, the more substitute carbon better tolerates positive charge and carries greater degree of positive charge. Positive charge, even though we indicate here being on bromine, is actually shared by 3 atoms of the ring, 2 carbons and bromine. And the greatest degree is on the most substitute carbon, because that one tolerates positive charge the best. So that's why where nucleophile will bond to the most substitute carbon of this 3-membered ring. And then we have 2 other reactions that proceed through cyclic transition states. One is oxymercuration demercuration. In this case, we use mercuric acetate. So we carry out 2-step reaction. First, oxymercuration. Oxymercuration means addition of oxygen, oxy, and mercury. So oxymercuration. So across double bond, oxygen adds. Oxygen forms 2 bonds, so it has to be OH. 1 bond to carbon added to hydrogen. So it's oxy, and then mercuration. We use mercuric acetate. So mercury remains bonded to one acetate group. So that's oxymercuration. And demercuration means removal of mercury. If it's removed, it has to be replaced with something. That's hydrogen. We use sodium borohydride, NaBH4. Potassium hydroxide is there only to stabilize the reagent, so it doesn't decompose in aqueous solution, and water is solvent. NaBH4 is source of H- hydride anion. So H- replaces mercury, and we end up with net addition of water across the double bond. Here is reaction mechanism, and you can see that this mercurinium cation ends up with forming cyclic mercurinium ion. And then again, backside addition results in oxymercuration. And then for this second part, how H- replaces mercury, you don't need to know the mechanism. So again, you can see just like bromination, same mechanism as bromination, the only difference is reagent, mercury plus. And overall result is addition of water across double bond. Water adds across double bond if there is selectivity, rigid selectivity involved, the same way as if carbocation were involved. The only thing is, of course, since this is cyclic intermediate, carbocations are not involved. So water adds following Markovnikov rule, or hydroxyl group ends on more substitute carbon, even though carbocations are not involved. And that's explanation here. It has to do with bond strength. More substitute carbon forms weaker bond to mercury. That's bond that is easier to break. Or in other words, that's the empty orbital that is lower in energy, and that's where oxygen tolerates free electron pair. So selectivity is the same as you would expect if carbocation were reaction intermediate. Difference is that unlike carbocations, there is no, you don't need to worry about rearrangements. So before we have covered rearrangements. So if reaction proceeds through carbocation, so we carry out reaction water in the presence of an acid, then compound like this, 3,3-dimethyl-1-butene, will undergo rearrangement. And so product will be rearranged product. But when we carry out reaction as oxymercuration, demercuration, then there is no rearrangement. So that's why we'll carry out this reaction, to avoid rearrangement. There is another important convention point, and that's this is two-step reaction. So we have to indicate two steps separately. So one, when we indicate this one, that means this is first reaction. This reaction is carried out to completion. When this reaction is done, then we carry out second reaction. If you omitted numbers 1 and 2, this would be wrong, because that would indicate that we mix all of this together. Mercuric acetate, water, and sodium borohydride. They would react with each other and nothing would happen to the alkene. So one means first reaction, 2 means second reaction. And sometimes we have 3, 4, and so on. So this is very important that you don't omit these numbers. And finally, hydroboration oxidation is the final type of reaction that we'll cover that proceeds through cyclic transition state. Hydroboration means addition of hydrogen and boron, and oxidation, that oxidation of the resulting product. Boron reacts in form of borane, BH3. That's electron deficient species because it has only sextet on boron, and so typically boron exists in form of diborane, or in a solvent, it's in complex with a solvent. But we always assume that it reacts as BH3. So we ignore what its actual structure, and simply we assume it's BH3. It's easiest to write down the mechanism that way. So an alkene reacts with borane, BH3, in such a way that boron adds to less substitute carbon and hydrogen to more. So BH3 adds to double bond in such a way that hydrogen adds to one carbon, BH2 to the other. And of course, since it's boron-hydrogen bond that adds across a double bond, we have 2 more bonds, reaction can occur 2 more times. So another BH bond adds in such a way that boron adds to carbon, hydrogen to more substitute carbon, and third time. We end up with trialkyl borane. Trialkyl boranes are actually highly flammable, not very useful compounds, but when we oxidize them with hydrogen peroxide, boron is replaced by oxygen, or OH group, and we end up with alcohols. And note that these alcohols have oxygen on less substitute carbon. And that's the way to make alcohols with oxygen on less substitute carbon, because methods we covered earlier, addition of water in the presence of small amount of acid proceeds through carbocation, and oxygen ends on more substitute carbon. Or oxymercuration, demercuration, again, oxygen ends up on more substitute carbon. Hydroboration oxidation is a way to end up with oxygen on less substitute carbon. So to have opposite regioselectivity and produce alternative alcohols. And don't be confused by rings again. We have 2 carbons. This is more substitute. It's tertiary carbon, less substitute, secondary. So hydroboration proceeds in such a way that boron adds to less substitute carbon. Upon oxidation, boron is replaced by OH, and we get this alcohol. If this alkene, 1-methylcyclopentene, were subject to either addition of water in presence of sulfuric acid, carbocationic reaction, or oxymercuration, demercuration, then product would have OH here. So product would have been 1-methyl cyclopentanol instead of 2-methylcyclopentanol. And here is explanation. Why do we observe this regioselectivity? Reason is steric. Boron adds to less substitute carbon because if it were to add to more substitute carbon, you see it would be like just like butane molecule, you would have this eclipsing strain between substituents. Eclipsing and torsional strain, both eclipsing and torsional strain. So that's why this transition state is less stable. It's much more stable if you have transition state where boron adds to less substitute carbon. Now, you can see that boron and hydrogens add to the same side of the double bond. Addition from the same side of double bond is called syn addition. Syn addition, that means same side. See, it says syn addition. It's addition from the same side. And so that means H and OH at the end, after everything is done, H and OH end up on the same side. This is a cyclic compound. They end up on the same side of the ring. And so that means that syn addition in cyclic molecules results in cis product. So just as anti and trans, don't confuse syn and cis. Syn addition results in cis product, but syn is mode of addition, cis is stereochemistry of the product. So don't confuse syn and cis. You need to know what is syn and what is cis. So syn addition, that's mode of addition, how to atoms add from the same side, and then product has substituents on the same side, that's cis. So syn results in cis, anti results in trans. Okay. And that's everything I planned for this lecture. So second part will be done next day.